Okay guys, in this tutorial I want to start talking about um, network inferences, and what we mean by that is so far we kind of looked at networks, and we kind of looked at how we can calculate certain features of the network. Like how many ties does a network have, like what's the density of the network, or what is the transitivity of a network. Transitivity is sort of like a way to kind of get to the number of triangles that are in a network. That's a measure that we have there. How many of those where let's say where A is connected to B and C, how many of those constellations do we also find a connection between B and C? And how many of those that could exist? And that's sort of like transitivity. It's a number from 0 to 1, while 1 means you only have these triangles, these transitive configurations, while 0 means you have no transitive configuration at all. But how do we know if a number, a network statistic that we calculated on a network, how do we know if the number is large? Or what do we know? I don't know, how do we know? Is it big? Is it a lot transitive? Is it a lot of triangles? Is it not many triangles? Is this more than you would expect to find by chance? Or is it less than you would expect to find by chance? So that's the kind of things that I want to talk to you about now. So one way of going about that, and now we're kind of bring in the last two tutorials together, because one way to do what we can do now is we can calculate a statistic, a network statistic on our network. That's what we're going to do. We're going to calculate transitivity on our LG network. Remember, that's this gang network that I imported in the first tutorial. So we can calculate that network statistic for that. And now we can go, and now we do something sneaky. Now we generate random networks. Random networks have the same number of nodes and the same number of ties as the original network. And then we look at the transitivity in these random networks. And that then can serve as a baseline to say whether the actual number of this, we call that the test statistic, the network statistic, whatever we care about, like in this case transitivity, whether the transitivity score, whether that is a lot compared to random networks, what you would assign in random networks. Why do we have to jump through these random networks? Well, because remember, the random networks have non-random network features, right? So the more ties you have, the higher your transitivity score will be. So in order to know whether transitivity score is high or not so high, you need to compare it against a random network that has the same number of ties and the same number of nodes. Because otherwise, what are you comparing it against? And then some people might say, okay, that still doesn't make sense to compare it against that, but that's a whole other thing. Let's talk about conditioning on the number of ties, and that's ultimately what we call the conditional uniform graph test. So the strategy or the recipe is very straightforward. Look up the slides I gave on that about hypothesis testing before. You calculate a network statistic on your network, something that you care about, like a number of triangles, number of ties between similar people, number of ties that are reciprocal, I don't know, overall average closeness score or whatnot. So like all sorts of things that you can calculate on the network. At the end, you get one number that characterizes that network, and then you want to compare that number to how that number would have looked like on random networks. And when there's a difference between that, then you can say, well, hang on, this number is really high here in my observed network. Meaning, like, if you have a transitivity score that is much higher than what your random networks would suggest, then you can say, hang on, there seems to be really a tendency towards transitivity in that empirically observed network that is more than just a chance effect. Or when you look at the number of ties between similar people, you might find, hang on a moment, there are a lot more ties between similar people than what we would expect to find by chance anyway. And then that's how you can then make inferences about that and say, okay, there seems to be a tendency for transitive triads or triangles or homomorphless ties in the network. Okay, so how do we go about that? Well, there's a command called gtrans. Let's look that up. That's like the transitivity command. And in the SNA package, compute the transitivity of an input graph or stack. Okay, when I do that, gtrans, that's like, that means like 36% of the configurations where there could be a closed triangle, there it actually is. I don't know why I said like equal sign, it doesn't really matter here. Let's go back to the arrow, it does exactly the same thing. So I save that in, now I have a number. Yeah, and that's now the test statistic that we care about. The number would be 0 if you would have no triangles at all. The number would be 1 if your whole network would consist of triangles. Let's do the same thing with density. gden is a command that does that. gden and parentheses and the network, and lgnet is a network object that we generated before. I assigned that to something that I called lgdensity. Now I have a number 0.092942. Yeah, that's the density of that network. How do we come about that network density? Well, if you kind of want to pause for a second, because there's actually an easy way when we look at our network. You know, we have our network, and then you see how many nodes we have and how many edges we have, and based on that, you should be able to calculate the network density. So maybe you want to pause and do that by yourself. Okay, let me just quickly show that, this is a little excursion, but why not, how I ended up with that value. So remember, we have that value LG density. How did we end up with that value? Well, our network has 133 nodes, ties, right? Okay. How many ties could exist? We have 54 nodes. And each node could be connected to each other node, so 5 times 53, right? And that would be a directed network. In our case, it's an undirected network. So that's why we want to divide that by 2. And voila, here's our network density. So that's how the network density came about. Anyway, so just a little excursion. So now we have these two numbers, LG trans and LG density. Let's extract another number, the number of network nodes. Well, we already know it's 54, but how do you actually get that? Let's say you have any network, a network of, how do you know the number of nodes? There's a very simple command, it's called network size. Network size returns the order of its argument, number of vertices. Okay. So network size, and I have a network called LGNet, I get 54. Great. So we kind of use that and we calculate that and we save it in something that we call LG size. So now we have something that is LG size. Same thing with edges. How can we go about edges? Well, now I calculated the edges. This is just a calculation, but there's actually another command. Network, is it edge count? Edge count, there we go. So that would be another way of extracting that. So here I'm just calculating things, I'm reverse calculating things. I could have equally just done network edge count LG net. That edge is 133. So now we have all the information that we need. We know how many nodes there are, we know how many edges there are in this empirically observed network, we know the density of that empirical network, and we know the transitivity score of that network. Transitivity score is how many triangles do exist out of the ones that could exist. Okay, so now we have all these things. Now we want to generate, remember, we want to know is this transitivity score a lot? Or is it less, I don't know, than what we would expect? Is it more, is it less than what we would expect to find by chance anywhere? So now the strategy is to say, okay, let's generate networks by chance. Networks by chance, and then look at the transitivity score. We don't want to just generate any network, because keep in mind, I don't know, there could be a network with 10 nodes, there could be a network with thousands of nodes. It doesn't really make sense to compare our small little network against all of these potential networks. So let's only compare it to networks that have the same number of nodes and the same number of edges as our observed network. So that actually makes a lot of sense, and that's what the conditional uniform graph test does. So now let's generate random networks that have these features. So look at this line. So what does this guy does? So RGNM, remember, this generates a random network with n being how many networks do you want to generate, and nv being how many nodes should there be. And now instead of just saying 200, which is what I've done before, or any other number, I use LG size. And LG size is what we calculated here before. So there's nothing else than 54. But you see, by doing it like that, it's a bit more elegant, because now I could run this with any other network. If you would hard code 54 in there, you would have to change that. But this is sort of a little more elegant way. And how many edges should there be? Well, m is the number of edges that the random network should have. And I say it should have LG edges. What is LG edges? Well, it's something we just calculate. It's 133. There we go. And it should be undirected network. That's what this one does. And it should generate 200 of those. And let's highlight that. And that's a nice thing. That was just really just a split second. And now what I have like this whole stack of, I don't know, 200 adjacency matrices. Let's look at the dimensions of that again. I often use the dimension command just to get an idea of what kind of matrix I'm dealing with. So now you see 200. So the first number indicates which one of those 200 networks you're talking about. And then you have for each one, you have like a 54 times 54 matrix. So this is a three-dimensional array, or a three-dimensional matrix. Internally it's saved as an array. And now we could go and now we can calculate for each. First of all, let's do something else. So now let's extract one of those. Yeah. So okay, keep in mind we use the brackets to subset something, and when we don't specify anything, just comma comma. Now I would just take the whole of it. Yeah? Keep in mind this is a three-dimensional matrix. So if I use 1 here, now it takes from the first dimension. So out of these 200, it takes the first one. And now nothing, nothing. So that means like basically all. Right? So what does that do? This gives me the first of those 54 times 54 adjacency matrices. When you look at the dimensions of that, you see now we have a matrix of 54 times 54. Now I could go for the second one. Now again I have these dimensions, but it's another matrix. Yeah? But each one of those corresponds to a random network that has 54 individuals, and that has in total 133 edges in it. So by using this one here, I basically take the first, from the first dimension, everything else on the second and the third dimension, which gives me one matrix of the size with a dimension of 54 times 54. So I use that as an input to generate a new network. It should be undirected. False, so I specify that here. I use the network command and I'm calling this adders first. There we go. Now I have a new network called adders first. It has 54 individuals in it and it has 133 edges in it. Yeah. So now we could actually go and, well, I don't know why this, let's say let's plot adders first. I could go and plot, so you see this is now a random network with 133 nodes, with 54 nodes and 133 edges in it. I can go and I can calculate let's look at that. The density of this network is exactly the same density as in our LGNet network. Why? Because we conditioned it on that. Yeah? We conditioned it on the number of edges and the number of nodes that it should have. And now I could go and now we could calculate the transitivity for that random network. Let's do that. G trans adders first. Now we have a transitivity score of this random network of 0.1. And we have the transitivity score of our LGNet network is 0.36 something. So that seems like, okay, hang on a moment. In our LG network, that already seems to be more higher transitivity score than a randomly chosen selected network. But we can't really tell. This could have been just a fluke. We have to go again. I don't know. We could actually do the second one. Let's change that. Now I'm changing that to the second network. And now I'm calculating the transitivity score for that. You see, now it's a different value. Yeah. Or let's take the third network. Of course, I'm still calling it adders first, which is a little odd. But you get the point. There's a whole distribution of transitivity scores that we could get. Maybe we can get the transitivity scores for all of these 200 networks that we generated. Well, actually, we can in a very straightforward way, because the gtrans command doesn't just only take one network. It's also very happy to take a stack of networks. Gtrans, when you look it up, it says dot and that a collection of input graphs. So it is absolutely fine to take a three-dimensional matrix here, where the first dimension indicates which network it refers to. And when we do that simple command here, Now, you see, instead of using AirDosh first, I'm using AirDosh graphs. And AirDosh graphs, what is AirDosh graphs? That is the outcome of that command here. That's essentially a three-dimensional, it's an array. It's a three-dimensional array with 200 entries on the first dimension, and then 54 and 54 on the second and the third dimension. So I'm running this command on all of them at the same time, and I'm saving it in something called AirDosh graphs trans. Okay, what is that? AirDosh graphs trans. Now you see, how cool is that? Now you have 200 entries, 200 values, each one corresponding to one of those 200 networks that we randomly generated. And each score tells you the transitivity score for that randomly selected network. So, you know, our very first network was really quite a coincidence that it was just zero, just really 0.1. I was a little struck by it, but actually it is just coincident. But then the next network had like transitivity, the next randomly selected generated network with 54 individuals and 132 ties has a transitivity score of 0.13. And then the next one has a transitivity score of 0.04 and so on. So now we got like a lot of random networks that all have the same characteristic, the same number of nodes, 54, and the same number of edges, 133, than our empirically observed network. But now the next thing is we want to, let's plot that. I don't know what I'm doing here now. Density makes like a density function out of that. And so you see in a second, okay, so this is what you get. So this is a distribution of that stuff. Yeah. It was on the histogram route. Let's go with the histogram route. Sometimes density plots are a little nicer. Right. You see, this is a histogram of the distribution of the transitivity score. So this is the transitivity score on this axis that you see, and this is how many of those random networks have a transitivity score that falls into this bin, basically, right? You see, like most have a transitivity score that is around, I don't know, 0.09. Some have a little higher transitivity, others have a little lower transitivity score. So what I'm doing here, in this command, I'm going back to the density function. You see, density function, that's like just making this a smooth line out of it, out of a histogram. Now I use another option called xlim. Xlim limits sets basically the, I don't know, which range should be plotted on the x-axis. And they say start at 0 and end at 0.45. You see in a second why I did that. So now it starts from 0 and it goes to 0.45. Before, it just starts somewhere and ends at wherever it has the highest value. Yeah. But now I want it to go all the way to 0.45. And I'm doing that because now I can add the line, with appline I can add a line to this graph with the original transitivity, with the transitivity score of the real empirically observed network that we have. And I'm changing the way it's being plotted. So I don't know, I'm making like a dotted here. Now you see this is the transitivity score. Remember, we had a transitivity score of 0.36 something in this gang network. That's the transitivity score. That's how many triangles we do observe in this gang network. This is the value that we empirically observe. And now you see these are the scores that our random networks came up with the same number of nodes and the same number of ties. What does this graph here tell us? Well, okay, it tells us the following. It tells us that, hang on, actually a random network sometimes you can generate a random network that only exists of triangles. It can happen. It's very, very unlikely, but it can happen. It's also a random network. That's like a network that only consists of triads is also a random network. It's just a very rare one. And it's equally rare as any other network as well, right? That's not as hard to grasp. It's also just a random network. So what is the chance that a random process came up with a network that has a transitivity score of 0.36? And that's what we can take from this graph here, that, I don't know, if I would simulate this instead of 200 times, like 1,000,000 times, some random networks would have a higher transitivity score. But then you can say, okay, actually it's only very few of those. In this case, none of it, right? And so basically comparing this line of our empirically observed network statistic with the network statistic that random networks would have of the same network statistic, conditioned on how many nodes, on the same number of nodes and the same number of ties as the original network, and tell us the likelihood that this value, the empirically observed value, is actually the outcome of a random data generating process. This is a long way of saying, well, if that line is so far out, it's really not very likely to have been produced by chance. And now we are in our 101 on hypothesis testing. Yeah? We can never say if something is really true or not. We can just really say, how likely is it that the pattern that we do observe has been produced by chance? And that likelihood is our p-value. That's what a p-value is. A p-value is nothing else than the chance that whatever value you observed is the outcome of a random data generating process. It's the same thing when you run a regression. You have like a regression coefficient and then you have a p-value. The p-value tells you what is the chance that a random process came up with a regression coefficient as the one that your regression gave to you. And when that number is really, really low, then you are confident in saying, okay, it's not just randomness that made that up. And that's really just a conditional uniform graph test. So right now I showed you the long way of doing a conditional uniform graph test. You calculate your test statistic on the network, then you generate random networks that have the same nodes and the same density as the empirically observed network. Then you generate the network statistic on all those random networks, and then you compare those randomly, there's network statistics on the random networks with the network statistics on the empirically observed network, and comparing that with each other, you can say whether there's something going on here, or whether it's just randomness that produced this number of triangles. Okay, so this was a long way of doing that. That's a much faster way of doing exactly that. And that's a command called CUG test. It's a conditional uniform graph test that I've just done. A conditional uniform graph test takes an argument, the original network, takes a function, in this case, G-trans function, in quotation marks. So for each one of those random networks, it calculates G-trans. It wants to know, is it a random network or not? Then it wants to have, like, I don't know, what it should condition on. In this case, condition it on the number of edges. And reps, like, how many random networks do you want to produce? In this case, I say 1,000. And if I do that, let's run these two lines. It takes a little bit, but there we go. We got an outcome. Univariate conditional uniform graph test. There we see our observed value. And now we see what is the chance that a random network would produce this test statistic. In this case, it was G-trans. Greater than our empirically observed one. Well, actually, there's a 0% chance here. Right? So if I would go if I go up 10,000, I don't know, maybe now we can find a random network. It's going to take a little. I regret doing this, because now it takes a little. Just want to see. Well, you see, even with 10,000 trials, with 10,000 random networks, we didn't produce a single network that had a transitivity score greater than the one that we observed. So that tells us something. Right? That tells us something that it's not really random. That score is not really random. So this creates a conditional uniform graph test object. There's a nice plotting command with that as well. Here we go. And that is really just the same plot that I've done before, just all in one package. So these two lines, really, you don't need to have the second one, do the conditional uniform graph test for you. But above, you have seen exactly how one would do that. Okay, let me add one last thing, and I'm going to end, because a conditional uniform graph test, you can also condition not just on networks, on random networks that have the same number of nodes and the same number of ties as the ones that you observe, but you can also condition on the dyad census. Remember, I was talking about mutual, asymmetric, and null dyads. In our case, it doesn't really make sense because the LG network is undirected to begin with. But here we go. If it would be a directed network, it would make sense. There, instead of C mode having edges, you condition on dyad census, and it does exactly the same thing. And now in this case, I don't know, it really did exactly the same thing as before. But if you would have a directed network, it would only generate random networks that have that many mutual relationships and that many asymmetric dyads. Really, just instead of using the random networks it would use the random network generated graph that I used before for generating random networks on a dyad census. This one. Yeah. So this RGU man generates random networks with a certain diode census. Okay, but bottom line, I hope you really get that point. That's like a conditional uniform graph test. You observe something in a network. You observe how many triangles there are in that network, and you want to know, is this a lot or is this not a lot? Yeah, or you want to know, is this just an outcome? Is this just a chance event? Yeah, that I don't know. This a network would have such a transitivity score. Because if you can confidently say that it's not chance that produced that, you can say, hang on, there's something else going on. So there seems to be a tendency for triads to form in that network, which makes theoretically a lot of sense. Yeah? When you commit crimes, you commit it in groups of the same people. You don't just commit it with random people, you commit it in groups. Makes a lot of sense. But how do we show that? Right? And the conditional uniform graph test is where you calculate a test statistic. In this case, we calculated transitivity. And then you generate random networks that have similar features as the observed network. In the conditional uniform graph test, we condition on the number of nodes and the number of edges, or we could even condition on the diode census. Yeah? Like only generate random networks that have these features, and then calculate all these test statistics for all these random networks again. You get a distribution of that. That's what you see here. That's the distribution of the test statistic for the random networks. And then you can compare it with your actually observed test statistic for the real network. And then based on that, you can say how likely is it that this line, this red line here, was produced, a network with such a high transitivity score was produced by chance. And in this case, the chance is actually look, it's almost zero. Yeah, we don't want to say zero because we know that if you would just go really, really high, if I would change that instead of to, I don't know, where is it? If I would, where is it? I'm confusing you. Conditional uniform graph test here. If I would go instead of to 10,000, would go to 1,000,000 or so. I'm not going to run this because this will run for quite a while. Then we most likely at some point we would generate a random network that has such a high transitivity score. But it's just really, really unlikely. Okay, so much about a conditional uniform graph test.